Welcome to the Deep Dive. We're your shortcut to understanding the big shifts happening in science and tech. And today, well, we're looking up, way up. We're diving into something that could really change how we deal with our nearest star, the sun. We tend to think of the sun as this constant, beautiful, steady, life-giving thing up there, calm. But if you get closer, it's anything but peaceful. It's this chaotic, boiling furnace. It's noisy, it's fast, and honestly, it's kind of rude to electronics. Just one big outburst from the sun, like a coronal mass ejection, where it throws plasma out, or a big solar flare, that can cause real problems right here. Stuff like scrambling your GPS, knocking out radio for flights over the poles. It can even push satellites around, mess with their orbits, and it can create currents and power lines that might trip breakers. Because blackouts. So yeah, this isn't just some abstract space thing. It directly affects you, your day, our whole connected world. For decades, predicting this space weather, well, it's been called more of an art than a science. It was this mix of physics, sure, but also guesswork, intuition. Really hard to nail down forecasts accurately enough.
That's exactly right. The unpredictability, it meant we were mostly just reacting, not really preparing. And what's so fascinating now is seeing that art, that reliance on gut feeling, starting to shift towards something much more disciplined, truly data-driven.
Right. And that's where this huge potential game changer comes in, NASA Surya. It's this new heliophysics foundation model. NASA co-built it using an IBM foundation model approach. Essentially, it learns from tons of high-res solar images over years, and now it can predict what the sun might do next. But, after decades of this art, some listeners might be skeptical. What's really different about Surya? What makes it so precise now?
Yeah, good question. The core difference is that foundation model approach. See, before, we tended to build very specific models, one for flares, maybe another for solar wind speed, very narrow tasks. Surya, though, it learns a general representation of how the sun behaves overall. Think of it like a brilliant student learning fundamental physics first. Once they really get those core principles, they can apply that deep knowledge to solve lots of different problems. That versatility is key. Surya isn't just about predicting one thing, it's about understanding the sun more holistically, which means you can then fine-tune it for many related jobs later on.
Ah, okay. So it's building this foundational intelligence about the sun itself, not just tackling one specific prediction. And it learns this from what you called a gold standard data set, right? 9 years of data from the Solar Dynamics Observatory, SDO. And this isn't just any data. Multiple instruments, different wavelengths, super high res, like 4096 by 4096 pixels, and captured consistently.
Exactly. The SDO is really the quiet hero here. Its record since 2010, it's just so consistent, so calibrated. That provides incredible stability for machine learning. Imagine watching the sun for almost a full solar cycle, seeing it through the exact same eyes, same geometry, day after day, for years. That consistency, it means less noise from, instrument changes or different viewing angles. You get more pure signal about the sun's actual physics. It lets Surya pick up on those subtle signs, those precursors to big events that might get lost in shorter or less consistent data sets. That's really why this data set is so rare and powerful. It's this stable, long-term view that lets the model truly learn the sun from the sun.
That consistent deep view really sounds like the foundation. Okay, so how does it actually see all this complex data? How does it interpret it to predict the future? You mentioned the technical heart is something called a spatiotemporal transformer. Sounds complex.
Yeah, it sounds complex, but the idea is pretty intuitive. Think of it like a really smart observer watching, say, a complicated dance performance. It's not just looking at one snapshot. And it's not just watching one dancer. It's tracking everyone's position on stage, that's the spatial part, and how their movements change over time, the temporal part, simultaneously. So for the sun, Surya tracks those evolving magnetic structures, the changing brightness in active regions, the plasma flows across the whole sun, and how they change minute by minute, hour by hour. It learns the patterns in that dynamic flow to figure out what's likely to happen next.
Got it. So it's like watching a high-def movie, understanding the plot, and anticipating the next scene. And the output. It's not just a probability score or something.
Precisely. And this is, I think, really fascinating. The result isn't just a number, which can feel a bit like a black box sometimes. NASA Surya can actually render an image. It can show you what a specific patch of the sun is predicted to look like a couple of hours ahead. And that visual output, it's incredibly important, makes the forecast inspectable. Scientists, operators, they can literally see what the AI is predicting. You can vet it with your own eyes before you fully trust the numbers. It's a huge step for building confidence in these kinds of complex AI systems.
Yeah, that visual check must be invaluable. Which brings us right to the next point. why Surya really matters, not just for scientists, but for, well, for you listening and for our connected world. We touched on it, but the stakes with space weather, they're incredibly high for our infrastructure.
They really are. When the sun gets rowdy, as you put it, the impacts are tangible. They're widespread. We're talking direct interference with GPS. Signals drifting by maybe tens of meters. That affects everything from farming to the timing signals for financial markets. Radio links can just vanish. That cripples communication for planes on polar roads, forcing them into costly reroutes. And those CMEs, the coronal mass ejections, they induce these powerful currents, geomagnetically induced currents, in long power lines. They can overload transformers, trip protection systems, potentially causing big blackouts, like the one in Quebec back in 1989.
And that directly hits your safety, your convenience. Airlines rerouting flights isn't just about cost, it's avoiding communication loss, higher radiation for passengers. And think about all those satellites in low Earth orbit, for internet, for weather, for defense. They have to actively boost their orbits during solar storms. Why? Because the atmosphere expands, creates more drag. Without warning, that extra drag can pull them down much faster.
Yeah, and if you connect all those dots, the main benefit becomes really clear. The faster you see these solar events coming, the less damage they cause, the less disruption, the safer and more efficient our systems can be. Surya aims to push that prediction window into a time frame that really helps for actual operations. It gives that critical lead time to mitigate risks. It's about moving away from scrambling after the fact towards proactive, informed preparation.
Shifting from crisis mode to smart prevention. Okay, but let's be clear. You said Surya is a research model today. It's not the official forecast you'd get from NOAA right now. So what's the path? How does it go from the research lab to actually being used operationally?
That's a really important point, the transition from research to operational impact. The good news is its whole architecture. It's specifically designed to support fine-tuning on downstream tasks. What that means is space weather centers, the ones doing the official forecast now, they don't have to rip everything out and start over. Instead, they can adapt Surya, integrate it into their existing systems, feed it their own specialized data, tailor it to their specific forecasting needs. You can kind of imagine a future service, right? One that blends Surya's AI predictions with real-time data coming in from other instruments and maybe traditional physics-based models too. This layered ensemble approach. That's how you build really robust forecasts. Ones that cut down on both misses failing to predict something and false alarms predicting something that doesn't happen. It's combining the best of the new AI with proven methods.
That sounds like a smart way forward, building on what works, adding these new capabilities. So let's get into the brain behind Surya a bit more. How does it actually learn? What's the core design philosophy for tackling something as, well, messy and dynamic as the sun?
Well, fundamentally, it's designed for scenes that evolve. That's crucial for the sun. It's always changing. Its transformer architecture uses a couple of key ideas to handle this. First, there's something called spectral gating. Imagine the sun's activity has these underlying rhythms, almost like musical notes hidden in the noise. Standard image analysis can struggle to separate those specific notes from just general brightness changes or background static. Spectral gating lets Surya sort of tune into specific frequencies of solar activity, filter out the irrelevant visual noise, and focus on the really critical patterns that might predict an outburst. It's more sophisticated than just tracking brightness.
Okay, so it's like teaching it to ignore the static and listen for the actual melody, however faint it might be.
Exactly. And the second idea is long-short attention. This lets Surya see both the small details, like an individual sunspot, or the complex magnetic loops in one active region, and understand the bigger picture at the same time. Like, what's the overall magnetic environment across the whole sun that this little region sits within? It keeps both the local view and the global context aligned over time. It understands how the small parts fit into and influence the whole scene. You need to see the trees and the forest for solar forecasting.
That sounds incredibly sophisticated. And the training process, how did they teach it to actually predict the future accurately?
The training approach was pretty clever in its simplicity. First, teach it to predict just one small step ahead, maybe a few minutes. Get that right. Then, you essentially roll forward that prediction capability for longer and longer time spans, like hours ahead. But here's the critical part. The training really emphasizes getting the structure right, not just matching pixels perfectly. What I mean is, if you just try to match pixel values, you might blur out important features or get hung up on tiny, meaningless fluctuations. Surya learns to preserve the physical shape, the integrity, the way solar features actually evolve. And the payoff is compelling. Surya generates these 2-hour visual forecasts that look remarkably similar to what the SDO actually sees later. That's the kind of result you can really check with your own eyes, build that trust before just relying on a number.
That visual verification is huge for trust. I get that.
Yeah.
Okay, so we know how it learns, why it matters. But what can Surya actually do right now? What are its tangible skills today?
Well, it's definitely not a one-trick pony. It's quite versatile. It can predict solar flares. That's crucial for radiation storm warnings. It can segment active regions, pinpointing those magnetically complex areas where most eruptions come from. It can estimate solar wind speed out at the L1 point, that's between us and the sun, giving us lead time on space weather hitting Earth. And it can even model the sun's extreme ultraviolet spectra, the EUV output. That's key for understanding impacts on our upper atmosphere and radio comms. Each of these is a vital piece of the whole space weather puzzle.
And it's not just doing these things, it's doing them better than previous methods, right? You mentioned some benchmark results. Like for solar flares, a 22% improvement in something called TSS. What does that actually mean for forecasting?
Right, TSS is the true skill statistic. It's a score that balances different kinds of success. It rewards correctly predicting flares that do happen, true positives, but it also rewards correctly identifying periods when flares don't happen, avoiding false alarms. So a 22% jump in TSS means Surya is significantly better overall. It's more reliable at telling us both when a flare is likely and, just as importantly, when it's unlikely. Fewer unnecessary alerts, more trust in the warnings we do get.
Okay, better reliability, fewer false alarms. That makes sense.
Yeah.
And for identifying those active regions, a 12% improvement in IOU, intersection over union, what's the practical benefit there?
IOU basically measures how well the predicted boundary of an active region matches the actual boundary seen by the SDO. So 12% improvement means Surya draws much more accurate, precise outlines around these key areas. For someone watching the sun, this means they can focus their attention much better. They know more precisely which areas are the most magnetically complex and where an eruption might start. More targeted analysis.
And there were improvements for solar wind prediction, too. 19% better RMSE, and EUV spectrum modeling, 12% better MAPE. How do those help?
Yeah, RMSE is root mean square error. For solar wind, a 19% lower error means Surya's predictions of wind speed are, on average, much closer to the actual speeds measured later at L1. That's huge for satellite operators. Better drag predictions mean better orbit planning, longer satellite life. And for EUV spectra, MAPE is mean absolute percentage error. A 12% improvement there means better predictions of the sun's ultraviolet output. Since EUV directly affects Earth's ionosphere, that means more reliable modeling of things like radio communication disruptions and GPS signal accuracy. Now, these specific numbers, they'll evolve as people keep working on this, but they definitely show significant jump.
These are clearly big steps up in performance across different areas. But like you said, it's not just the scores, it's that the outputs are interpretable. Those images you can check against reality.
Exactly. That interpretability is so important. It lets scientists actually investigate why a forecast might have been wrong.
Yeah.
Understand the failure modes, not just celebrate the wins. That whole cycle of inspecting, learning, improving, that's how you build forecasting systems you can really depend on.
And speaking of building trust and robust systems, a really crucial part of this whole Surya effort is how open it is.
Right, let's talk about that. Open science, open opportunities. This whole thing is being built out in the open, which sounds incredibly powerful. It really is. And it's how public science infrastructure should be built, I think. In NASA Surya, its code is on GitHub. The model weights, the data sets, they're on places like Hugging Face. This openness is fantastic because it benefits the whole community. Researchers can verify the claims easily. They can add new tasks, publish improved results faster. It speeds everything up. Students, they can get hands-on experience, run experiments, learn real heliophysics. That helps train the next generation. And industry teams, maybe satellite operators or airlines, they can test how to integrate these ideas into their operations and share what they learn. It creates this collaborative ecosystem.
That collaborative, open approach sounds like the key to making rapid progress. And it was a real partnership that made Surya happen, wasn't it?
Absolutely. It was a fantastic example of synergy. IBM brought their deep engineering know-how, their experience with foundation models, and the tooling to make it practical. NASA, of course, provided the critical mission focus, the scientific questions, and crucially, the stewardship of that amazing SDO dataset we talked about. That data is just fundamental, and the National Artificial Intelligence Resource Pilot Program was also key, providing access to the significant computing power needed for this kind of work. It really shows how combining these different strengths, government, industry, research infrastructure, can tackle huge challenges that maybe no single group could handle alone.
It's a great model. But even with all this potential, this collaboration, it's important to be realistic. You mentioned limits to respect alongside the opportunities to grab. It's still early days for this software.
That's a critical message for listeners, yes. Surya isn't a magic box you just plug in to replace today's operational forecasters. Not yet. It will still make mistakes, sometimes confident mistakes, especially when the sun does something really weird or rare that wasn't well represented in the training data. So the responsible way forward is integration. Use it within a layered system. Have guardrails, have monitors checking its performance, and always clear human oversight. Things like building dashboards to track its accuracy and its calibration, like how well its stated confidence matches reality, and keeping logs of weird events. That's essential for using it safely and effectively. It's a powerful new tool, but it needs intelligent human guidance.
So integrate it smartly, augment human expertise, don't just replace it. But the opportunities to build on this, to apply it, they seem huge.
Oh, absolutely. Wide open. You can imagine pairing Surya with data from ground-based telescopes, looking at the sun's magnetic field in detail, or with coronagraphs that actually see CMEs leaving the sun, or with brand new instruments coming online, all making the forecast richer. You could blend its predictions into flight routing tools for polar flights, making them safer and more efficient, or use it to improve satellite drag forecasts during stormy periods, helping keep our orbital infrastructure safe. And every new use case, every new data set you connect it to, it doesn't just help that specific application. It potentially improves the core model and strengthens the whole community using it.
This really feels like more than just a space weather story, doesn't it? Even if you're not a solar physicist, understanding this kind of project, it opens up thinking about how AI can tackle other really complex real-world problems that used to seem almost impossible to predict. So let's wrap up this deep dive. The core idea here is that NASA Surya is pushing space weather forecasting from that intuitive art towards a much more rigorous, data-driven science. It's literally learning the sun from the sun, using years of incredibly detailed, consistent imagery to let an AI find the complex patterns that predict solar fury.
And the potential impact is really broad, affecting aerospace, energy, telecoms, navigation, so many areas. By giving us better, more interpretable forecasts with more lead time that actually matter for operations, Surya can help make our technology-dependent world significantly more resilient to the sun's moods, enhancing safety, improving efficiency.
Yeah, this whole deep dive really shows how AI, especially these foundation models, are becoming powerful tools for decoding some of nature's biggest mysteries. It really makes you think, doesn't it? Consider this approach. Training foundation models on huge, consistent data sets to predict complex, evolving systems, how else could that be applied here on Earth? Could similar models change how you interact with things like weather forecasts or maybe climate change predictions or even understanding patterns in your own health data in the future? The sun's definitely going to keep throwing puzzles at us. But now, thanks to innovations like NASA Surya, we've got some powerful new ways to start solving them.